Hello, I'm Binghai. Today we are going to talk about a new topological phase called Topological Crystalline Insulator. It is a topological phase protected by the crystal symmetry. And the crystal symmetry here, especially, I will refer to today is a mirror symmetry, the topological invariant called mirror Chern number. It is a topological phase. It will have a metallic surface states if the surface preserves the mirror symmetry, like the top surface, but the other surface, if the mirror is breaking, and then it's insulating. I assume you already learned about the topological insulator, and let's revisit this topological insulator part. Its bulk band structure can be created from a band inversion. After the inversion, spin-orbital coupling gap the band crossing, and we get a new topological insulator. Here, the topological invariant called Z2 index. This Z2 index, it can be 1 if there is a parity switch between the valence and the conduction band. And that, for simple, we count the parity in the valence band if we get in total minus an odd number of minus, and then it's topological. If it's an even number, it's trivial. The consequence of this band inversion is we will have the topological surface states. The surface states cross each other at the center. Here is time Russell invariant. Therefore, time Russell will protect the band crossing. In 3D, the Dirac cone, the center point, protected by time Russell symmetry. And here, the TI give us a beautiful picture. Here is in the bulk, we have a topological invariant, protected or defined by time Russell symmetry. On the surface states are protected by time Russell symmetry directly. And we have a one band inversion, we get one Dirac cone. And follow this logic, let's do some experiment. Like very simple, let's simply double all the bands. We double the valence conduction bands, we double the number of band inversion. After that, if you count the parity, actually we have 2 minus. Therefore, this is trivial. It's not a topological insulator, and we cannot use this topological invariant. It's trivial here. But we still ask the question whether there are interesting surface states. Follow this picture. We have one band inversion, we get one Dirac cone. Now we have two band inversion, then we have two Dirac cone, right? Now the question is, these two Dirac cone, they will intersect with each other. For example, they will cross each other here. Whether this crossing point is robust or is protected by something. We know in quantum mechanics, this band degeneracy usually requires symmetry protection, additional symmetry. In a TI case, this symmetry is time Russell symmetry. But however, here, these 2 points, for example, they are not time Russell invariant point. There's no time Russell to protect. If there's no any other symmetry to protect them, actually, these two Dirac cone intersect each other, then they get fully gapped. We have a band gap here. And if we are lucky, or in some special case, maybe there's a symmetry protect some points, this still gapless. This gapless point, like, may come from, for example, a mirror symmetry. And let's see, like our logic is, we start with a double band inversion. This double band inversion, we ask on the surface whether this double Dirac cone will be robust. If it is robust, maybe we need a mirror symmetry. There's a mirror plane in the bulk, but on the surface still preserves the mirror. If the mirror cross this double Dirac cone, the crossing point, they may remain gapless. And if so, this is a mirror protected surface states. Yeah. Then here, later we will learn about this new topological invariant called mirror Chern number, because here, this ordinary time Russell Z2 number does not help us anymore. Now let's look at closer to about this mirror symmetry. We look at the mirror symmetry simply a mx mirror flip x to minus x. Here is a little special for spin. Actually, this spin apply on sx does not change the sign, but y and z, they will flip. And we can understand the spin simply from if we look at the spin as this self-rotating current. After the mirror symmetry, this self-rotation does not change direction. But if it's parallel to the mirror, this self-rotation will change the direction, right? That means the spin flip sign. That means the spin x and minus x direction, they are eigenstates of this mirror operator. And then this about they will have different mirror eigenvalue, plus I minus I. Actually, you see this imaginary number. This imaginary number, we can understand it from here. The mirror symmetry can be regarded as a combined C2 rotation with inversion. Inversion will do nothing to spin. After inversion, spin does not change. But C2 simply means we get a pi rotation. Yeah. For ordinary states, we get a pi rotation simply means we get a minus sign, like from x to minus x. But for spin, because spin is a special quantity, spin, the angular momentum is 1/2. If we make a pi rotation, actually the total phase the spin will pick up is 1/2 pi. The 1/2 pi rotation will exactly means we will get an imaginary number. This is imaginary number I. And if minus pi, you see it minus 1/2 pi, we get a minus I. And this is the reason we get this imaginary number. And in other words, if we consider the full wave function, actually the mirror symmetry will always guarantee the mirror symmetry. Can be classified into two groups, plus and minus I, with the opposite mirror eigenvalue. Let's look at the surface states. If the surface states cross the mirror plane, actually here, these two and the other two, they have different mirror eigenvalue. Now you see immediately, because the crossing, these two states, they are orthogonal to each other. They have different mirror eigenvalue. Therefore, they don't have to hybridize and open a gap. And this is the meaning of mirror protection. And this is how mirror works on the surface. And for topological states, we learned that if something happens on the surface, or there are some special surface states, and usually it has an origin from the bulk. Therefore, we look at the bulk states. And since mirrors, like surface states, we can classify them according to their mirror eigenvalue. We can do the same for the bulk states, right? And now let's look at the bulk states inside the mirror plane. Now it's a 2D plane. Inside the mirror plane, the bulk states, it's an insulator, because now we always talk about insulating bulk. And if we have a time also symmetry together, actually now in the mirror plane here, all these states, they will be double degenerate. They double degenerate because of mirror symmetry. And this plus minus I have opposite eigenvalue. And we know they are orthogonal. Now we can simply separate these plus I states and minus I states into two subspace. These two groups, these two states, they don't hybridize each other because they are orthogonal. And now let's only look at one subspace. And what we said here, this is because it's a 2D insulator. This 2D insulator, we already learned from this quantum Hall effect or Chern insulator. For 2D insulator, we can always define a Chern number, and a Chern number for all the valence band. For example, this Chern number is n plus I minus I for two subgroup. If we have time also symmetry, time also tell us the total Chern number will be always 0. Yeah, for simple, if we have time also symmetry, we don't have quantum Hall effect. But if n independently, n plus I, for example, is equal to 2, and that still means something. And we can define another mirror Chern number that's simply a difference between n plus I and minus I. Here, for this relation, we know they are always opposite in sign. If n plus I is 2, then in total, the mirror Chern number is also 2. Then what's the physical meaning of this number 2? And now we simply need to come back to the Chern number. And for example, if we have a Chern number 2, we learned from quantum Hall is if Chern number 1 means we have one chiral state. If Chern number 2, that means we will have two chiral states, right? That simply means on the boundary of this 2D mirror plane. Now we are talking about the boundary of the 2D mirror plane. It's a 1D edge states. We will have a two chiral edge states. Their chirality is always right moving because it's plus 2. And the same logic for Chern number minus 2, we get opposite two chiral states. Now, if we look on the boundary, put them together, these two, we will see these four edge states, kind of two pairs of helical states. And we already know these states, they don't open a gap here because of mirror protection. And their topological origin is indeed from the bulk. From the bulk, from this bands in this subspace, every subspace, this band has a Chern number. Therefore, it has chiral states. Then, because Chern number is 2, it will have 2 pairs of chiral states. And if Chern number is 1, we have 1 pairs. We get something similar to the topological insulator. And let's summarize this actually. We always start from the bulk states. Like the topology tells us, to understand the boundary, we think about the bulk. Usually that is enough. And this is the bulk eigenstate. This is the eigenvalue. The eigenvalue function, because we have mirror symmetry, we can always classify them separate them into plus I, minus I, 2 subgroups. These 2 subgroups, we can define them independently, 2 Chern number, because 2 subgroups are 2 insulators. If the mirror Chern number is non-zero, that tells us it will have a chiral edge state. And now let's look at this 3D picture. If their bulk, the bulk, this inside this blue mirror plane, we have a non-trivial mirror Chern number. It guarantees on the surface, we will have a, on the surface or here, on the surface, when it intersects with the mirror, it's a 1D line. Along this line, there are chiral edge states. These chiral edge states, actually, they are directly corresponding to the crossing point of this Dirac coin. That means the top surface is gap place, because there's a mirror symmetry on the top surface. Now, naively, we can understand on the side surface, if this surface, we don't have mirror symmetry, then we don't have to mirror protection, then we get a fully gapped. That means now we get a 3D insulator. This insulator is top surface is gap place, but its side surface has a band gap. And also interesting, you can see is here, the hinge. Here, the hinge is the boundary between these 2 side surface. Is metallic because there's a mirror across this hinge. This hinge state is a 1D state. It's interesting, right? If we look at the cylinder, all the surface is insulating, the bulk is insulating, but this hinge is metallic, and it's a 1D state. And this is actually such topological phase called higher order topological insulator. About a higher order TI, we will learn in the following lectures. And here, today, I give you an example. It's about this mirror topological crystalline insulator. The mirror symmetry help us to define a topological invariant and protect the boundary states. But for crystal symmetry, we know then it's not only mirror. We have rotation, we have skew rotation, we also have glide mirror. Actually, they can all help us to define some special topological crystalline phase. And this is, we call it usually quite like, see, topological crystalline insulator protected by specific symmetry. And there's a systematic way to classify this TCI phase. And there's a method called symmetry indicator. You will learn in the following lectures. And there you will see a systematic picture. And this mirror TCI is a very representative TCI system. And in the later lecture, you will learn specific material to realize it. For example, tin telluride, and all their surface states has been verified in experiment.